All right, so the people, here's the situation. Uh, we're going to be trying to find the expectation values of position, momentum, position squared, momentum squared, and um, the standard deviations thereof for the first and second, um, that is the ground state and the first excited state of these quantum harmonic oscillator, right? Um, we're also going to be looking at the expectation values of kinetic and potential energies towards the end there, but those are just going to be exercises of the Iron Fist theorem. So this ground state wave function for the simple harmonic oscillator is m omega over pi h bar to the 1/4 exp minus m omega x squared over 2 h bar. Um, and I'm not going to write the first excited state just yet. I'm just going to do stuff to this for now. So Griffiths gives us a couple of different definitions of variables to work with in this problem, and I'm going to do that as most as I can. So we have alpha being defined as m omega over pi h bar to the 1/4, so this prefactor, and we have c being defined as the square root of m omega over h bar dx. No, just x. Haha. X. Um, so that means given with these variables, it's very easy to rewrite psi 0 as being alpha times e to the minus c squared over 2. And with that, we'll simplify the process of finding the first, or the ground state expectation value of position, defined as the integral over all space of the complex conjugate times x times the wave function dx. So it's going to look like alpha squared times that integral. And since the wave function is real, they just kind of multiply together like this. And you get x times e to the minus c squared dx. We do have to change that x, though, over to c using this equation here. It's just not too hard to do, a little bit of algebra. You just invert the prefactor. So we have alpha squared times the square root of h bar over m omega there. And now we're doing the integral over all space of c times e to the minus c squared dc. And actually, to get the dc, we need to take the integral, or the derivative of this to get the new differential dc equals to this thing, m omega over h bar dx. Yeah. Okay, yeah. So because dc is what it is, we'll actually have two of these h bar m omegas over here multiplied together. So just a one whole power. And we have dc. That is a table integral, and it is 0 because that's a odd function multiplied by an even function. So that is 0. I'm going to go ahead and say out loud that the first, or the ground state expectation value of momentum can be found with Iron Fist theorem, and it's also going to be 0. So that is perfectly chill. We'll just need to find now what the ground state expectation value of position squared is, which is a little bit more rigorous. So again, now we just have x squared in there. So it's looking like the expectation value of, we got x squared times e to the minus c squared dx. And then changing x into c and changing dx into dc, we'll have alpha squared times h bar over m omega to the 1/3. And we'll have the integral minus infinity to infinity of c squared e to the minus c squared dc. That is also a table integral. I'll just write it here. Integral over all space of u squared e to the minus u squared du is just root pi over 2. It helps that there's actually nothing in the exponent except for the variable c squared. So it is that simple. Root pi over 2. So this is looking like alpha squared h bar over m omega. It's not 1/3 though. I don't know why I said that, because it's 3 halves. Because it's 3 radicals multiplied by each other. And this is root pi over 2. I'm going to expand the definition of alpha. So alpha squared will be the square root of m omega over pi h bar. And then factor out one radical from the 3 halves term and leave the other one as just a complete power, h bar over m omega. We still have this root pi over 2. But now this pi cancels out this one, h bar cancels, m cancels, omega cancels, and we just have h bar over 2m omega. That is a lovely result. Going further, all we need now for the ground state is the expectation value of p squared, which is minus infinity to infinity star p psi dx. That's p squared, actually. And so the squared momentum operator is minus h bar squared over 2m times the second derivative. So we have, now it's minus alpha squared h bar squared. We have the integral from minus infinity to infinity. And then we have the wave function, which is c squared over 2. And then also the second derivative with respect to x, e to the minus c squared over 2 dx. So now we not only have to change the dx into dc, we also have to change the derivatives into derivatives of c, which isn't too difficult, because we're just going to use the chain rule for derivatives and say that we're going to have an extra factor of dc dx, 2 of them, and then this becomes the partial derivative with respect to c twice on the exponent. Now plugging in what we have for dx, and also looking back up here to think about what dc dx is, it's just the square root m omega over h bar. We're going to have 2 times, so m omega over h bar square root squared. So you'll just have it m omega over h bar. And then you'll also have the factor from changing this dx to dc, which is just root h bar over m omega. And then now we can start thinking about doing derivatives on this thing. Oh no, del squared del c squared e to the minus c squared over 2 dc. Simplifying the prefactor a bit, we have minus alpha squared m omega h bar. Let me just write it like that, and then this will be h bar over m omega. Over here, we'll do the first derivative. It's actually just minus c times the exponent. So we can factor out the minus sign from in there, actually, so this isn't minus anymore. We can expand the definition of alpha. It'll be alpha squared will be the square root of m omega over pi h bar. We'll still have the m omega h bar. We'll still have the square root h bar over m omega. In the integral, we'll do the next derivative, which is going to be one factor will just be 1. The other will be minus c squared, and we'll have e to the minus c squared over 2 dc. Simplifying the prefactor, we have this cancels this, this cancels this, this cancels this. So it's just m omega h bar over root pi. And then we're going to split the integral into an integral of minus c squared dx and an integral of c squared e to the minus c squared dx from minus infinity to infinity. The second integral we've already done. The first integral, very simply, I'll write it here because it might come in useful later. The integral over all space of just a Gaussian is just root pi. Okay. So this is going to be root pi. This is going to be root pi over 2. So the root pi cancels, and we just have m omega h bar times 1 minus 1 half, which is just 1 half. So m omega h bar over 2. And we can go ahead and check that the uncertainty principle for the ground state is satisfied. So we'll just multiply sigma x, which is going to be the expectation value of x squared, which we found was h bar over 2m omega, minus the expectation value of x, and you square that, but that was 0, so that's done there. And then sigma p will be the expectation value of position squared, which we just found, minus the squared expectation value of momentum, which was also 0, so that's done. And then this cancels this cancels this. We have h bar over 2, which we square and then take the square root, so it's just h bar over 2. So cool, the Heisenberg uncertainty principle is satisfied for the ground state. wave function. Awesome. Now I have to look at the first excited state, do the same thing. Um, actually, let's hold off on that. Let's think about what the energy is going to be um, for this. So specifically the kinetic energy. Um, if we wanted to calculate the expectation value of this, it wouldn't be uh, that hard at all, actually, because it's just p squared over 2m. That's the expectation. No, that's the kinetic energy operator. This is for general states. Um, but if you already have the expectation value of p squared, then that's what this is. It's 1 over 2m times the expectation value of p squared. So it's just 1 over 2m times whatever you got for the expectation value of p squared. So we have that the expectation value of kinetic energy for the ground state will be 1 over 2m times m omega h bar over 2, and this m cancels out this m, and we get h bar omega over 4. Similarly, if you wanted the expectation value of position or of potential energy, the potential energy for a simple harmonic oscillator is very simply given by m omega squared x squared over 2, right? And then none of that stuff in there are operators except for x, so we can factor out an m omega squared over 2, and we'll still have the x squared in here. And we already have the expectation value of x squared. So this is for general states, actually. Specifically for the ground state, we got that the expectation value of x squared was just h bar over 2m omega. And then 2 doesn't cancel out, actually. But we get the same result as we got for the expectation value of kinetic energy, which is kind of a proof of virial theorem, but it's even more satisfying whenever you actually add up the kinetic energy and the potential energy, which in theory should give you the overall energy, and it does do exactly that. It takes care of the energy for the ground state. So, pretty cool stuff there. Back to work, though, we had to do all of that again for the first excited state. We have that the first excited state is m omega over pi h bar. It's the 1/4 times square root of 2m omega over h bar x times the ever so awesome exponent term. We're going to go ahead and try and represent that in the notation of alpha and xi. That is going to look like alpha xi times root 2. So root 2 alpha xi times e to the minus xi squared over 2. Yeah. Okay. And so expectation value of position for that is going to look like 2 alpha out front. And then we'll have in the integral an x times xi squared times e to the minus xi squared dx. And we'll change that x over to a xi and the dx to a dxi by multiplying by h bar over m omega. So we'll have c cubed e to the minus c squared dc. This is also 0, right? Polynomials to the odd number give you an odd function, which if you integrate it will give you 0 every time. So fantastic, we took care of that handily. Now we need to do the expectation value of x squared, which, as you know, psi 1 star x squared psi dx. For us, that is going to look like 2 times alpha squared times h bar over m omega to the 3 halves, because we have to convert both of those powers of x into xi and also dx into dxi. Integral over all space of xi fourth e to the minus xi squared dxi. And at this point, it's worth introducing. I think this is the last table integral that we had to look at, but it has to deal with Gaussians that are multiplied by its arguments to the fourth, which is given by the square root, or 3 times the square root of pi over 4, right? So we have that form. Just apply it here. 2 alpha squared h bar over m omega 3 halves times 3 root pi for 4. Expanding the definition of alpha and canceling out the 2, we'll have 3 root pi over 2 times square root pi, or square root m omega over pi h bar. And then we'll have, we're going to do the same like moving around trick before in the 3 halves term. So we're just factoring out a radical and leaving the rest separate. So h bars cancel out, m's cancel out, omegas cancel out, pi's cancel out. So we just have 3 h bar over 2 m omega for the expectation value of x squared for the first excited state. Now we have to do p squared, and this is a long one. Also, the expectation value of p through Ironfest's theorem again is 0. So don't even worry about that. P squared, we're going to be pulling out minus h bar squared, right? We'll have xi e to the minus xi squared over 2 d squared dx squared xi e to the minus xi squared over 2 dx. And we have to convert the second derivative over x into a second derivative over xi by multiplying by the derivative of xi with respect to x twice, and also change the differential over into dxi, so we multiply by an additional factor of it's just h bar over m omega. If you don't like the letter Xi, I apologize. Because this is looking like Xi e to the minus Xi squared over 2 d, or now this is a partial derivative, partial squared partial Xi squared, Xi e to the minus Xi squared over 2 d Xi. So we happen to know that the derivative of Xi with respect to x is just the square root of m omega over h bar, and we're doing that twice. So one of them is going to cancel out this square root. The other one will stick around. So we'll have the root m omega over h bar there, and then in here we're going to do the first derivative of the stuff with respect to Xi, which shouldn't be too bad. We'll have a term proportional to 1 as well as a term proportional to minus Xi squared, multiplying the, that looks like a zeta now. I'm getting lazy. Xi squared over 2 d Xi. Going ahead and expanding the definition of alpha, m omega over pi h bar. That'll definitely help things out front, I think. And now this stuff in here is just getting chaotic really quickly. So the derivative of e to the minus Xi squared over 2 is just minus Xi. We'll have minus 2 Xi, and you'll also have a positive Xi cubed, all multiplying the exponent. Right? Yeah. I'm getting really tired of all these X's now. Simplifying the prefactor a bit, we just have we just have h bar squared over root pi. But then these guys combine into just m omega over h bar. So that's nice. We're going to split up the integral, actually. We're at that point where we can have a integral of Xi cubed times e to the minus Xi squared. And it's not cubed, it's to the fourth, because there's an additional Xi out front. Xi fourth e to the minus Xi squared d Xi minus, and it's actually minus 3 times the integral of Xi squared e to the minus Xi squared d Xi, from minus infinity to infinity. Simplifying the prefactor again, we have minus h bar m omega over root pi. Over here, these are both integrals that we've seen before. This is just 3 root pi over 4. We have minus 3, and then that's an integral we've seen before. That's just root pi over 2. Right? So let's kill the root pi's. So you have minus h bar m omega. I'll factor 3 out. And so we have 1/4 minus 2/4, which is 1/4 again. So 3h bar m omega over 4. I don't think I did that right. I dropped a 2 way early on. Whoops. So this is going to be -2. There's a 2 here. There's a 2 here. There is a factor of 2 here. So this is actually minus 3h bar m omega times minus 1/4 times 2, which is just 3h bar m omega over 2. And that is kind of a nice result. Again, we'll look at the Heisenberg uncertainty principle for these. The expectation value of x squared was just 3h bar over 2m omega. Expectation value of p squared was, we just found it, 3h bar m omega over 2. And so we have, bam, no, actually base bar doesn't cancel out, and neither does any of the numbers. It's literally just the masses and omegas that cancel out, so we just get a 3h bar omega over 2, which is certainly bigger than h bar over 2, so Heisenberg uncertainty principle is good. We can look at the kinetic and potential energies as being using the same trick that we did before, 1 over 2m times the expectation value of p squared, which is going to be 1 over 2m times 3h bar m omega over 2. So it's 3h bar omega over 4, funky style. And then this is m omega squared over x squared, no, over 2 times x squared, right? So we have it that it's m omega squared over 2 times 3h bar m's on bottom. It's 2 m omega on bottom. One of those omegas get canceled out, the m goes away. We have 3h bar omega over 4, so they're the same. And also they add up to make 3h bar omega over 2, which is the energy of the first excited state. So everything's looking good for the quantum harmonic oscillator. All right.